Okay, sampling distribution of the mean, and we're going to look at central limit theorem. We've got an introduction to it, and we had a classroom investigation and we came up with some of these observations. Okay, so we're going to build on what we did in class. Learning goals are going to discover the properties of the sampling distribution of the mean and introduce the central limit theorem. Okay, so we looked at an example, pretty straightforward example about IQ, and we know that mu for IQ equals 100, the mean of the population, and standard deviation is in fact 15 for IQ. So we are assuming a normal distribution here, keep things fairly straightforward. Let's investigate the properties of the sampling distribution of the mean via simulation. So the sampling distribution of all of the means, we started off with size 10, so the sample size was 10, so we had basically 10 people chosen at random and found the mean, and we had a whole bunch of examples, and we did more than just two, but here's two examples. Okay, so these X bar statistics are different, and the fact is they vary. So the mean of each sample, or in other words the sample mean, is actually a variable. It's a random variable because we're randomly choosing the things that populate each of these samples, okay, the people chosen at random. This is because well, that's a unbiased way of choosing something, so it's a random sample, hence a random variable. X bar is a random variable, so the sample means are random variables, or the X bar, the variable, is called a random variable. Okay, and this is called a sampling distribution. When we look at how all of the different values of X bar come together, that's called a sampling distribution. And what we did was that we looked at different sample sizes. We looked at what happens as we increase our sample size. So we looked at quite a few samples. We took 200 samples using technology, and basically the first time we did it we had n equals 25, so each of these samples has 25 of the calculation of this nature here. That's only 10, but imagine 25 numbers there divided by 25. That's the same mean process that we've got there. So we did that 25, and then 100, and then 200. So that's 200 samples, each of size 200. Alright, so it's 25 sample size, so we had 200 samples of size 25, 200 samples of sample size 100, and then 200 samples of sample size 200. Okay, so that's what each of the dots mean. And we observed that how the distribution looked, okay, once we increase n the sample size. So the value of n is quite significant. What we've got here is what's called Rice Virtual Lab in Statistics, or RVLS. Okay, just acknowledging the website. It's called onlinestatbook.com, and we're looking at sampling distributions now. Probably just the top of it's probably just out of shot there, but we've got basically a population, or a parent population here. Alright, so you've got your parent population here, and you might not quite be able to see the peak of it in shot, but it's a normal distribution. Alright, so it's got that normal shape. Okay, that's a terrible drawing. That's a shocking drawing, but you know what if you're watching this video, you know what a normal distribution looks like. Okay, that actually looks skewed. It's not supposed to be, it's normal. And basically we can use this animation to just show a few things really quickly. It's quite possibly out of shot, but the mean, it says, is 16. So the population mean mu is 16, and the standard deviation of the population for this one is 5. You'll have to trust me there. You might be able to see the 5, but the 16 is out of shot. Now let's play some sample data here. So can see some sample data entering. And what we're going to do is compare the distribution of the means. You can see here I've got n is set equal to 5 and then n a lot bigger at 25. Now 25 bits of data, sample data, have occurred here. Okay. Now I'm going to add some larger amounts to this, and we've got an extra 10,000. Okay, so 10,001 trials. So I forgot to show you what it's like if we have 5 of those repeated. So you can see then that we've got the first one that I animated and another 5, which makes 6. Okay, so instead of a mean of what we had before, which was 16, you might recall, okay, we have in here for the 2 different sample sizes, let me just get my pen working, we have for n equals 5 we have a mean of 13.31 and a standard deviation of 6. And remember earlier I wrote down here 16 for the mean and the standard deviation was 5. Okay, so what have we got there? We got 13.3 and down here 13.09 versus 5.89. So they're not the same, are they? That's after 5 plus the original sample, 6 samples. Let's add another 10,000 onto that. Okay, so you can see now that the mean is 15.92 when n equals 5. And when n equals 25, it's actually 16, like the population, the parent population. Okay, the standard deviation 2.24 and 1.04. So the standard deviation seems to be approaching 1 for the higher number of, or the higher sample size. They're both approaching the population mean. Let's try another 100,000. Okay, so we'll add that in, and I've actually added another 200,000, but that's fine. So we've got both cases, the mean is 16, or it's actually 15.99 there for n equals 5. It's awfully close, and 16 there for 25. The standard deviation is 1 here, and it's not approaching 1 there. So that's interesting, isn't it? What we're going to see in this video is that the as we get towards finding the mean of sample means, the value of the mean of the sample means, which we'll see in a minute can be written like that for 1, that will approach the value of the population mean, especially in a normal distribution. And the standard deviation of the sample means, which can be written like that, or it can be written like this, and I'll show you it properly in a minute. Same thing. That will approach the population mean over the square root of n, the sample size. Alright, and so we see that originally the sample size up the top for the population, if you can just see that there, it's 5. So this one here would be the standard deviation for the sample means would be 5 over root 5, because 5 is the standard deviation of the population, root 5 is the square root of n, and that's about 2.24. Try it yourself with a calculator and look. So again, this one here will be 5 over the square root of 25, because n equals 25 here, and that's 1, so that's approaching 1. So why do we have this apparent trend? Indeed, we have the different values of n plotted against the standard deviation of the means. Okay, so you can see these two here were in the simulation. You can even plot that, and it does follow this formula here. where that's the standard deviation of the population on the top there. It's 5 in this particular case, and it has a perfect correlation. Interesting. Well, before we go and formalize this, let's have another look at another quite simple example. But let's consider a very small population this time, because this helps us show the difference between a normal and a distribution that's not necessarily normal. Okay, so we've got a very small population and an even smaller sample, and let's assume the population describes, it doesn't matter what it is, let's say it's the mass of something, okay, because I'm going to talk about this thing called variability in a minute, okay, and recently I experienced a real life example of variability. So it would suit me at the moment to say, let's assume that it's mass, but it can be anything continuous with continuous data, I guess. So let's say this population describes the mass of something, some product or something in grams, okay? Consider the following data points. So here we go. The mean of these points is 21.8. You can verify that yourself. Standard deviation is 11.16. So that's the population. All right, I told you it was very small. Okay. Now we're taking sample. What about the sample? We're taking sample sizes of 2. So n equals 2. That's ridiculously small. So this is a case where an extreme can really help build confidence in a concept. So we've got here 23 and 42. So these are all the possible combinations of getting these two right through to 21 and 12. And here we found the mean. So the mean of 23 and 42 is 32.5 right up to the last one. Okay, so we've got high variability, haven't we? We've got high variability is evident there because the sample means, remember, it's described by x bar. It jumps around quite a bit, doesn't it? It varies quite a lot. It's 32.5 there, 17.5 there, and so on and so on. So we have high variability is evident, and it could be intuitive for you to really see that, yeah, we are likely to get high variability with only 2 in the sample. Okay, but it perhaps, or more than perhaps, we probably understand that it will be reduced with larger samples based on our previous studies and our intuition. Okay, so it's okay to use your mathematical intuition. The thing about this data that I haven't told you, it's actually normally distributed. So the mean of the sample means, so the mean of x bar, now that is written, it's often written as expectation or expected value of x bar, or sometimes mu subscript x bar. It's actually, if you find the means of all of these numbers here, right through to the end, all of those, you get 21.8, which is the same as the population mean. All right, the population mean is 21.8, and so is the mean of all the sample means. Okay, the tendency for the mean of the sample means to be the same as the population mean is known as the central limit theorem, and that's exactly what it is for normally distributed data. Okay, for a normal distribution. By the way, the standard deviation is of the sample means, the standard deviation of the sample means, so of all of these means of the samples, is written usually with sigma subscript x bar or SD capital X bar. It's, as we saw in the simulation, it's actually sigma over square root of n, and it's 7.89 for that above data. Okay, so that's a second important thing. Okay, so the first one was this paragraph here, if you're taking notes. Okay, and the second one is that one on the sample mean standard deviation. As the standard deviation is divided by the square root of the sample size, the measure of variability becomes smaller as the sample size increases. I'm going to cross now, when that's validated by that simulation earlier, by the way, because as the sample size increases, did you notice that the n equals 5 and the n equals 25, all right, there was a difference there. That one there had less variability. You saw the the result of the sample standard deviation gets smaller and smaller. Remember, it was approaching 1, okay, and this one was approaching something quite a bit larger than that. So that's that variability. And if we cross over to some photos, recently when I was looking at some small packets of pretzels that were to go in a kid's lunchbox, we looked at the sample, a sample of 2, because there's 2 kids, right? And one packet felt different to the other, and I looked on the back and it's supposed to be 25 grams. One of them was 28 grams and the other one was in the 60s. So that's quite amazing, isn't it? That's a good example of variability. Okay, so this stuff exists in the real world. Anyway, if the population is not normally distributed but the samples are sufficiently large, something really cool happens. Okay, so what if it's not a normal distribution? So we looked at normal distribution there, but what if it's not? If the samples are sufficiently large, then the sample means will also be normally distributed with a mean of mu, just like above. So the mean of the samples, the sample mean, all right, which remember is written like that, that equals mu. Okay, the other way of writing that e to the x, remember, is like that too. Either way is fine. Okay, they'll both equal the population mean, and the standard deviation will be sigma over square root of n. So the standard deviation of the sample means, or like that, okay, they will both equal the population standard deviation over the square root of n. Okay, now the verification does exist and it's based on some previous work you would have done in math methods, and it is not essential, so don't, unless you're doing this video for some higher level stat at university or something, don't copy that down, but it's just showing that, hey, this can be verified based on some of the formulas you've seen in the past. Cool stuff. Next video is going to be on some worked examples.